All right, let's dive into one of nature's most powerful and honestly paradoxical forces, radioactive decay. I mean, this is a process that's both life-saving and incredibly dangerous. So we're going to break down how it all works. So let me ask you something. When you hear that word radioactive, what's the very first thing that pops into your head?
Yeah, for a lot of us, it's probably this, right? That feeling of danger. You see that iconic symbol and you just know it's a warning about some kind of powerful, invisible force.
But, that's really only half the picture. Radioactivity is a classic double-edged sword. On one side, yeah, it's this destructive force that can mess with our cells and DNA. But on the other, it's an unbelievably precise, life-saving tool that's at the heart of modern medicine.
So to really get our heads around this, we've got to go back, way back, to the beginning. When radioactivity wasn't a tool or a weapon, it was just a complete and total scientific mystery.
Okay, so picture this. The late 1800s. It was just this whirlwind of scientific discovery. It all kind of kicks off with X-rays. But then, things get really weird. A guy named Henri Becquerel finds that some uranium salts are, well, they're exposing photographic plants right through solid black paper. I mean, how does that even happen? This crazy puzzle is what set Marie and Pierre Curie on the path to discovering even more powerful elements, and it opened up this whole new world of energy.
And that was the absolute core of the mystery. Where was all this energy coming from? It seemed to fly in the face of the most basic laws of science. I mean, they were looking at two possibilities, and both were just unthinkable. Either the law of conservation of energy was just plain wrong, or something even crazier was happening. Atoms were literally changing from one element into a completely different one.
Well, it turns out the answer wasn't about breaking the laws of physics. It was about discovering a whole new layer of physics, hidden deep, deep inside the atom. Okay, quick refresher. At the heart of every single atom, you've got the nucleus. It's packed with protons and neutrons. And here's the key rule, the one thing that matters most. The number of protons tells you what element you're looking at. 6 protons, always carbon. 7, always nitrogen. That number is like its fingerprint. It's non-negotiable.
But, and this is a big but, the number of neutrons can totally change. We call these different versions isotopes. So, take carbon. Most of the carbon out there is carbon-12, and it's perfectly stable. But if you add just 2 extra neutrons, you get carbon-14. It's still carbon, chemically speaking, but now it's unstable. It's radioactive.
And boom! This is the answer to Marie Curie's puzzle. Think about it. In a normal chemical reaction, like burning wood, all you're doing is shuffling electrons around to rearrange atoms. The elements themselves stay the same. But in a nuclear reaction, the nucleus itself changes. The number of protons can actually shift, and you can literally turn one element, like carbon, into another, like nitrogen. That old alchemist's dream, transmutation, it was real.
So this whole process of spontaneous change, that's really the heart of it. You have an unstable parent atom, like our carbon-14, and it just decides on its own time to release some energy and particles to become a more stable daughter atom. That whole transformation, that's what we call radioactive decay.
Now you'd think something spontaneous would be totally random and unpredictable, right? And for one single atom, you'd be absolutely right. There's no way to know exactly when it's going to decay. But, and here's the crazy part, when you get a whole bunch of them together, their behavior is incredibly orderly. It's super predictable.
And the way we measure this predictability is with a concept called half-life. It's pretty simple, actually. It's just the amount of time it takes for half of your sample to decay. So let's say you start with 160 grams of something radioactive. After one half-life, boom, you've got 80 grams left. Wait for another half-life to pass, and now you're down to 40, then 20. It just keeps following this perfect, predictable curve.
The amazing thing is at this time period, the half-life is a constant for every single isotope. Some decay in the blink of an eye. We're talking fractions of a second. Others, like certain types of uranium, have half-lives that last for billions of years. And it's this incredibly reliable, constant rate that turns radioactivity into a seriously powerful scientific clock.
And of course, the most famous example of this is carbon dating. Here's how it works. While we're alive, you and me and every living thing, we're taking in a tiny bit of that radioactive carbon-14. But the moment an organism dies, it stops. And that's when its internal carbon-14 clock starts ticking down. So by measuring exactly how much is left, archaeologists can figure out the age of ancient artifacts with incredible accuracy.
But remember, that whole decay process, it's releasing a ton of energy. And that brings us right back to that double-edged sword we were talking about at the very beginning.
You know, the early pioneers of this field, they learned about the dangers the hard way. Even Marie Curie, who would eventually die from a disease that was almost certainly caused by her years of exposure, she gave this very stark warning about radium, the element she herself discovered.
So what exactly makes it so dangerous? Well, the high-energy particles that get shot out during decay, think of them like microscopic cannonballs. They're what we call ionizing radiation. That just means they have enough power to literally knock electrons clean off of any atoms they smash into. And if that happens inside your body, it can break chemical bonds, damage your cells, and even mutate your DNA. It's serious stuff.
And yet, despite all that, we perform over 50 million nuclear medicine procedures every single year around the world. It's incredible. We've actually learned how to take that same dangerous power and use it to heal. So the question is, how did we pull that off? How did we manage to turn this powerful natural force from a hazard into one of the most vital tools we have in all of modern medicine?
Well, the answer really comes down to two words: control and precision. Today, this technology is so common that about 1 out of every 50 people in developed nations gets some kind of nuclear diagnostic procedure every year. It's become totally essential to how we do healthcare.
It's like we've built this amazing nuclear toolbox with different isotopes for different jobs. You need to do a diagnostic scan? Okay, we'll use something like technetium-99m. It's got a short 6-hour half-life, which is perfect, just long enough to get the pictures we need before it safely vanishes. Need to detect cancer with a PET scan? We'll use fluorine-18 with its even shorter half-life. And if you need to actually destroy a tumor, that's when we bring out the heavy hitter cobalt-60. Its longer half-life gives us that powerful steady beam we need for radiotherapy.
I mean, what an incredible journey, right? From just a mysterious glow on a photographic plate to a fundamental force of nature we can now use to see inside our own bodies and fight off terrible diseases. It just goes to show you, when we truly understand and master a process of the universe, we can completely rewrite the rules of what's possible. Makes you wonder, what do we master next?